Okay, so for the second part of section 5.2, we're going to look at a few more trig identities, but a little more complex. So this first one, we're still verifying that the left side equals the right side. And so the first one says 1 minus cos theta over 1 plus cos theta. When we take the square root of that, that's equal to 1 minus cos theta over the absolute value of sine theta. Now we'll talk about where that absolute value comes in at the end. So I would say when we're thinking about which side looks more complex, I would say the left side. Right? There's more to do. There's a square root. There's a fraction. There's a little bit more to do. So we'll work on the left side and just prove that it equals the right side. So this is what we're looking for. We have to kind of refer back to that periodically. So right now we have 1 minus cos theta over 1 plus cos theta. There's not much to do. We can't change it into sine and cosine terms because it's already in those terms. So I would say again, multiply by the conjugate of the denominator just to get some squares in there and possibly use the Pythagorean identities. So I still have this square root, but I'm going to take what I have and multiply it by the conjugate of the denominator. So 1 minus cos theta. Right, and I didn't really change the value because I'm really multiplying by 1, so this is fine. And it's all under the square root still. So when I multiply on the numerator, 1 minus cos theta times 1 minus cos theta, I'm just going to put that together since there's two of the same binomial as 1 minus cos theta squared. Denominator, I have to use a little FOIL because they're not exactly the same. So 1 times 1 gives me 1. 1 times negative cos is negative cos. Cos times 1 is positive cos. Negative and positive cancel out. If you need to see that, go ahead and use FOIL or box method and multiply it out. And you'll see that the middle terms here cancel out. And then lastly, cos times cos gives me cos squared. Okay, so then I look to see, well, what can I do? I still have this square root. Can't move that away yet. But I see that I have something squared and I have a possible Pythagorean identity. So if you go back and look at the Pythagorean identities, this is one of those, right? So we took cosine squared plus sine squared and rearranged it, and we saw that sine squared equals 1 minus cos squared. So I'm going to rewrite this as just sine squared since it's equivalent. So now I have 1 minus cos theta, all of that squared, over sine squared. And now I can deal with getting rid of the square root. A square and a square root cancel each other out. Same on the numerator and denominator, because this square root is essentially on the numerator and on the denominator. So it'll cancel here, and on the numerator I'll have 1 minus cos theta. I don't have to worry about any absolute value because 1 minus cos theta is always positive. Right? If I think about cosine, its range is between -1 and 1. So whether this is a -1 or a +1, this value is always positive. So I don't have to worry about absolute value. It's the denominator when my square root and squared cancel out, that sine theta is not always positive. I do have to make sure that I'm saying I only want the positive answers. When I square sine here, it turns my answer positive, and then square root, I still end up with a positive solution. So I have to make sure when I'm simplifying, I still would get the same sign that I originally would have gotten the original equation. So now I have 1 minus cos theta on the numerator over sine theta, the absolute value of that on the denominator. So now I have shown that the left side equals the right side. All right. Next one says use a calculator to verify and then verify algebraically. So we've just been verifying algebraically. Right? We're showing all our algebra skills and verifying on paper. Let's look at the calculator to see how we would verify. So it says 4 tan to the 4th plus tan squared minus 3. This is equal to sine squared x times a quantity of 4 tan squared minus 3. So if I'm using a calculator to verify, I'm trying to verify that one equation, this side here, which I'm going to write as 4 tan 4x plus tan squared minus 3, that equation, when I graph it, is the exact same picture as this equation, secant squared x. If they're supposed to be equivalent, when I graph them, the picture should be exactly equivalent. Okay. So let's go to Desmos and just look at the graphs. All right, so I typed in 4 tan x to the fourth plus tan squared minus 3. Okay, when we look at that graph, we see this is what it looks like. And if it's supposed to be equal to secant squared times this quantity of 4 tan squared minus 3, I should get the exact same picture. And so this picture is in blue. So if I take this off, it is in blue. But when I combined it with the previous picture, because they're exactly the same and they're right on top of each other, the purple and blue are turning, sorry, the red and the blue are turning to purple. So we see that the graphs are exactly the same. You can take one off. There's one graph. There's the graphs together. They're exactly the same. So that does verify that the two equations are equivalent because their graphs are exactly the same. Okay. So then when I come back here and verify algebraically, so we use the calculator, we verified. When I verify algebraically, I'm going through and looking at what side looks more challenging, right? And then determining, well, what can I do to prove that the left side equals the right side? I don't necessarily know that one side looks more challenging. You could do some factoring here on the left and prove that it equals the right side with some identities, or you can just look at the right side and use some identities. I'm going to start with the right side and start simplifying on the right to prove that the right side equals the left side. So if we look at the right side, I have secant squared times 4 tan squared minus 3. Secant squared is the only kind of difference here. I have a 4, I have a 3. You know, the sign is not the same, but we can hopefully adjust that in the end. What I want to do is take this secant squared and take it out and replace it with a trig identity. When I go back and look at my Pythagorean identities, there's one involving secant squared. Okay, and so we go back and look and we see that secant squared is equivalent to tan squared minus 1. Correction, it's equivalent to 1 plus tan squared. So let's change this guy. And all I'm doing is using our little Pythagorean identities from section 5.1 to rewrite equivalent forms. Okay, so then 4 tan squared minus 3. Now I have only tangent and numbers here, and that's exactly what the left side has. So we just have to multiply using FOIL to verify that we get exactly the same expression. So 1 times 4 tan squared gives me 4 tan squared x. 1 times negative 3 just gives me negative 3. Tan squared times 4 tan squared gives me 4 tan to the fourth. I'm just using my exponent rules, adding the exponents. And then lastly, tan squared minus 3 gives me negative 3 tan squared x. Okay, so then if I look, the only like terms I really have is the tan squared x's. So I have 4 tan squared x minus 3 tan squared x. Okay, should kind of include this in here. Minus 3 tan squared x. So that gives me tan squared x, and then I'll rewrite everything else down. Minus 3 plus 4 tan 4x. All right, and of course this is not in ascending order or descending order. Here, if I write everything in the right order, I'm going to have my 4 tan to the fourth x first, and then I'll put my plus tan squared, and then I'll put my minus 3, which then verifies that yes, the left and the right side are exactly the same. So we have shown that this identity is verified and true.